Welcome back, Calculus 2 students. In this video, we're going to expand upon our discussion of exponential growth with the logistic model, which has a different looking differential equation, a modification of the differential equation we looked at before. So let's motivate this a little bit. Why would we have this new funky looking equation? If we examine the exponential function in its graph, we can see that after initial growth, the growth is going to accelerate and give us an unbounded growth that's faster and faster and faster. And that's exactly what we were looking for before. We wanted something that was proportional to the amount. Well, in a lot of applications, after an initial period of exponential growth, we expect some kind of leveling out based on a carrying capacity for an environment. So there's only so high this population can grow. We want our curve to asymptotically approach that. And the differential equation here is designed to model that in some way. Notice that whenever y is very small, close to 0, inside the parentheses we have an expression that's close to 1, and therefore without this expression here, the remainder looks like the exponential differential equation that we solved before. On the other hand, as y gets very close to the carrying capacity k, the numerator of this is close to 0, and that makes the entire derivative approach 0, hence the flattening out of the curve. And so our task is to solve this differential equation to get a function whose graph looks more like this than this. All right, so we begin in the same way as before. I'm going to divide both sides by some of this content we're looking at here. If I want to separate my variables, I'm going to go ahead and write a dy. I will divide by y and also k minus y. But I'm going to multiply by k on this side, and over here I will just leave the r. So once again, we have a separation of variables. The y is on the left, the x is on the right. Constants can go wherever you find them convenient. On the left, I'm going to integrate using partial fraction decomposition. Notice the denominator here is a y times k minus y. I want to leave it to you to write the steps of the partial fraction decomposition. So you might pause the video at this point, see if you can work this out on your own and get the answer that I get. So I'll wait. Having done that, what we should end up with here is 1 over y plus 1 over k minus y. This is easy to check if you multiply these together to get your denominator, and then k minus y on top here, y there, combine them, you'll get k. Let's go ahead and anti-differentiate the right-hand side. That's the easy part. And now on the left, we have natural log absolute y plus, well, no, it's a minus actually, natural log absolute k minus y. And the reason we have the minus there is because of the chain rule and or substitution involving k minus y. Now I want to use logarithm rules in order to combine these into a single logarithm, because that's going to make it much easier for me to solve for y in the long run. It's also easier for me to think of k minus y on top of y. I can separate into separate fractions and do all kinds of things a little nicer. I have the benefit of hindsight with this. That may not be obvious to you right now, so you can try it this way. But I like to actually invert my subtraction a little bit here. In order to do that, I'm actually multiplying by -1 to switch the order. So I need to multiply by a -1 on this side to keep it consistent. On the left, I have this expression. On the right, of course, still minus rx minus c. As before, I'm going to raise both sides as an exponent on the number e. Now the e to the minus c, just as before, is just a nice constant. And so we're going to take care of this and the absolute value simultaneously as before by giving it a new name. I'm going to use the letter A, and the A is going to absorb that e to the minus c as well as any sign change that results from the absolute value. On the left, I can separate k over y and y over y. I can add 1 to both sides. And now to solve for y, I'm going to reciprocate. And finally, multiply by k. Now, if this equation also had an initial value, we could use that initial value to solve for a. And that's going to depend on both k and the value that's provided. I'm going to stop here with the logistic model, though. My main reason was, number one, to give you an extension of what we did with exponential growth. Number two, to give you yet another example of solving a separable differential equation. But also number three, to give you some familiarity with this terminology that's showing up in a lot of videos right now about the spread of viruses. So in the next video, I'm going to pick a little more or less random differential equation to solve by the separable method that won't have this context. But if you are watching other videos and you hear about the logistic model, this is likely what they're talking about. It is a function whose graph is going to have earlier behavior, like the exponential function, but then level out over time to asymptotically approach some horizontal line representing the carrying capacity for that population. Until next time.